Hello students, welcome to 8th session of electrochemistry. In this session, we'll discuss about the electrolysis using an example of fused sodium chloride. We'll also look into the electrolysis of water. Then we'll discuss about the factors affecting the products of electrolysis using the example of electrolysis of copper sulfate using different electrodes like platinum and copper. We'll also understand the concept of overpotential using the example of electrolysis of aqueous sodium chloride and look into the various application of electrolysis. What is electrolysis? Electrolysis is a process of decomposition of ionic compounds into their respective elements by passing electricity. Now let us understand this using a very familiar example that you studied in your earlier classes. Let us look into the electrolysis of fused sodium chloride. When electricity is passed through fused sodium chloride gets decomposed into metallic sodium and chlorine gas. At anode, oxidation takes place, and at cathode, reduction takes place. We can remember this using a simple mnemonic, that is red cat and ox, which is nothing but a small mnemonic to remember. At cathode, reduction takes place, and at anode, oxidation takes place. Reduction is basically gaining of electrons, and oxidation is losing of electrons. At cathode, cation, that is Na plus ion, accepts an electron, gets reduced to metallic sodium. At anode, anion, that is Cl minus ion, losing its electron, is converted into chlorine gas. So at cathode, sodium is liberated, and at anode, chlorine gas is liberated. Now let us consider another familiar example, that is electrolysis of water. When electricity is passed through water containing a small amount of acid or alkali, oxygen is liberated at anode and hydrogen is liberated at cathode. Why water containing small amount of acid or alkali is used? That's because the pure water is a non-electrolyte. It does not conduct electricity. Therefore, as such, it cannot be electrolyzed. Therefore, a small amount of acid or base, around about 20%, is needed to carry out this process. Here again, at anode, oxidation takes place, and at cathode, reduction takes place. At anode, the anion is oxidized, and at cathode, the cation is reduced. At anode, oxygen is liberated, and at cathode, hydrogen is liberated. Since at each electrode there is only one anion and cation, so this is not a very complicated. If on the other hand there are several anions and cations, then the product of electrolysis will be different. That we will be discussing in our next slides. of electrolysis depends upon three factors. One is the nature of electrolytes. You know that during the electrolysis, anion move towards anode and cation move towards cathode. So the electrolytes should be in their liquid state. Apart from that, the product of electrolysis will also differ. The electrolytes are in their molten state or their aqueous solution. The next factor is the nature of electrodes. Electrolysis can be carried out using various different types of electrodes. One of them is inert electrodes such as platinum, or even sometimes gold is used. These are the electrodes which do not participate in the chemical reactions. Whereas when the electrodes used are active metals, they will participate in the chemical reaction and undergo oxidation or reduction depending upon the electrodes. Let's understand this using an example of electrolysis of copper sulfate using platinum and copper electrode. During the electrolysis of copper sulfate using inert electrode like platinum and in the another case use the copper electrode, you can see that in the both cases at cathode the copper ions gets reduced. This is as per their reduction electrode potential. At cathode, thermodynamically, the one with higher reduction electrode potential gets reduced. Now, if you look into their standard reduction electrode potential, it is very clear that the copper is having higher reduction electrode potential. It's reduced in preference to H plus ions because it is a copper sulfate solution. So the water is also present in the solution. In both the cases, whether it is using the platinum or copper, you can see that copper is deposited. But when you look at the anode, the things are not same. In the case when platinum electrode is used, there are two anions. One is OH minus and other is SO4 2 minus, that is hydroxyl ions and sulfate ions. At anode, we know that oxidation occurs. So the ion which has lower reduction electrode potential will get oxidized. Therefore, if you look into their reduction electrode potential, we see that OH minus gets oxidized to O2, that is, oxygen is liberated at anode. Whereas when copper is used as electrode at anode, there are three possibilities. One in which the reduction electrode potential is lower will be preferred, which you can clearly see that it is nothing but the copper. As we have already known that if electrodes are not inert, they will participate in the reaction. Also, since copper is getting deposited at cathode, the concentration of Cu2 plus decreases in electrolyte. So in order to compensate that, the copper at the anode starts dissolving into the copper sulfate solution. That is, the copper at the anode is oxidized to Cu2 plus ions, and it moves towards the cathode and gets discharged. That is, it gets deposited at the cathode. This is exactly the principle that is used in the electrolytic refining of the metal. The third factor on which the products of electrolysis depend is the electrode potential of oxidizing and reducing species. This we have already seen in our previous example. At anode, if there are more than one species or more than one anion, thermodynamically one with lower reduction potential is oxidized, and at cathode, thermodynamically the one with higher reduction electrode potential is reduced. But these need not always be true because there are exceptions. There are several electrochemical processes which are thermodynamically feasible but kinetically very slow. Hence, in order to make these processes occur, extra potential, which is also known as over potential, must be applied. This we will see through an example in our next slide. Now let us look into the electrolysis of sodium chloride solution. In the case of sodium chloride solution, two anodic and cathodic reactions are possible. At anode, we know that oxidation takes place. So thermodynamically, one with lower reduction potential will have the preference to be oxidized. At cathode, since reduction takes place thermodynamically, since our electrode potentials are reduction electrode potential, therefore one with higher reduction potential will be preferred. At anode, the two possibilities is one is the reduction of chloride ions into chlorine, the other is the reduction of water into oxygen. Although as per our reduction electrode potential,
oxygen should be evolved at anode. But this does not happen. This is the exception. Why? Because thermodynamically oxygen is preferred, but kinetically the oxygen needs more potential than the theoretically calculated value, because the reaction is very slow. So more potential than thermodynamically stated value is needed. Hence, the chlorine is liberated, chlorine gas is liberated. Whereas at cathode, here there is no such problem. Hence, we can see that the one which is thermodynamically feasible takes place. So, although thermodynamic feasibility is important, but kinetics it also plays an important role in determination of product that is evolved or the products of electrolysis.
Now let us look into some of the applications of electrolysis. Electrolysis forms the basis for the manufacture of various chemicals. We have seen that in the manufacture of caustic soda, brine, which is sodium chloride, is electrolyzed. Hydrogen is evolved at cathode and chlorine is liberated at anode. It is carried out in a Castor-Kellner cell where mercury is used as a cathode. In the manufacture of potassium permanganate, potassium manganate is electrolytically oxidized. Also, for the manufacture of potassium hydroxide, white lead, which is basic lead carbonate, used as a white pigment in paint industry. All these chemicals are synthesized electrolytically. Electrolysis also have wider application in industries. For example, in the production of hydrogen by the electrolysis of water, for the extraction of reactive metals, that is metals having very high negative reduction electrode potential. These are usually the metals which are above zinc in the electrochemical series, which cannot be reduced using any other reducing agents. These metals are potassium, magnesium, aluminium, sodium, etc. Another application of electrolysis is the manufacture of deuterium oxide, which is heavy water, which is used as a moderator in the nuclear reactors. Nonmetals like hydrogen, fluorine, chlorine are obtained by in the electro refining of metals, as we have discussed in the electrolysis of copper sulfate using copper electrode. The impure metal is made anode and the pure metal is taken as cathode. During the electrolysis, the pure metal are deposited at cathode. In electroplating, coating superior metal on the surface of an inferior metal to increase the corrosion resistance is known as electroplating. So these are some of the applications of electrolysis.